We'll get started. Thank you very, very much for coming to the talk and for coming to PostgresOpen. So we're talking today about Postgres indexes in a very fast survey of Postgres indexing techniques. Feel free to ask questions during. I may cue those for the end, depending on how the complexity of the question and how we're going on time. Just really quickly, my name is Christoph Pettis. I'm the CEO and lead consultant for PostgreSQL Experts. We're a boutique Postgres consultancy based in near San Francisco, California. If anyone knows where Alameda is, that's where we are. That's my email address. That's the URL of my personal blog. The slides will be up there within the next week. And there's my Twitter account. So indexes. We don't need indexes by definition. Because an index, by definition, cannot change the results of a query. It can, you can be 100% compliant with the SQL standard and not implement indexes. So why bother? There's a lot of, indexes are a lot of work. Let's just skip that part. The problem is this, that the order n operations problem. Because operations that take order on are bad. Not as bad as on squared, but the problem is that without indexes, all queries are at best sequential, because it has to pick up every row, rattle it, see if it matches the predicates, and then throw it away if it doesn't. This is really bad. You can imagine, billion row table, that kind of thing. Even worse, you're doing a join on two tables that are each a billion rows. And if this was an order n by m operation, you could see that this would get out of control very, very fast. The whole point of an index is to turn this on into something better than n, ideally log n or order 1 or something like that. But just a reminder, possibly the most common question we get about query optimization is, why isn't it using my index? And very frequently the answer is because using your index would be a bad idea. They're essential for database performance, but they do not result in speed improvements in all cases. So it's important to match the index to the particular queries and the workload and what you're doing. And getting some ideas about how to handle that is what we're talking about today. So let's look at Postgres' amazing indexes. Postgres has lots of different index types. There's B-tree. Everybody knows about B-tree. There's hash indexes, gist, gin, spgist, Brin indexes, a relatively new addition, and Bloom indexes. So we'll talk about each one and what it's good for. But we have this really wide range of index types, and each has a range of query types and workloads and data types that they work well for. But how do you know which one to use? We should give a talk on that. So here we are. OK, B-tree indexes. This is the most powerful algorithm in computer science, and no one knows why it's called that. Are they for balanced or broad or Boeing or bushy? Is it the algorithm that came after A-tree indexes? We don't really know, actually, why they're called B-tree. They're old enough to be a lot of people's parents. The first paper about them was published in 1972. This is where the idea that it stands for Boeing comes from, because the original inventors worked for Boeing. It's the default index type in pretty much every other database everywhere implements B-trees, because it really works really well for a large number of cases. Everyone's seen this graphic about how B-trees work. It's as the word tree might imply, it's a tree structure with bins, and it partitions the index, the total range of values, into buckets, which then go down. So this says everything from the start through 7 is in this one. Everything from 7 and 16, inclusive or exclusive, now I don't remember. Whatever. Goes to this one, and everything higher goes into 18. B-trees have a lot of advantages. They tend to be very shallow structures compared to other tree structures, like a binary tree or something like that, which means that you have to pull fewer disk pages out to complete a walk of the tree. They provide order log n access to leaf nodes. Yay, we're in the good range of orders. And they're totally ordered, so you can walk them in ordered directions. So you can help with they can help with merge by and order by, merge joins, excuse me, other operations that require sortation. The original B-tree paper had a fixed number of keys in each of the buckets. That doesn't work for Postgres because Postgres has lots and lots and lots of different data types with highly variable sizes. So Postgres B-trees have a variable number of keys per node. And the entire index key is copied into the index because it needs to do a comparison on them. Which means that larger values, if you have a 32-bit int versus a UUID, say, you'll have fewer keys possible per node because the nodes themselves are fixed size. So you'll get deeper indexes. So they will perform not quite as well if you are indexing larger data types. Okay, we're done. We've solved the indexing problem forever. Not so fast. Problem 1, the entire key is copied into the index. You know, if you have 288,000 byte character strings, this isn't so great. Who knows what toast is in Postgres? Okay. The short version is toast is how Postgres has a hard limit to how wide each row can be in bytes. It's 8K, by default, it's 8K minus some things. You can recompile Postgres to change this, no one ever does that. The problem is, of course, we often want to start more than 8K things. Toast is an auxiliary table that is effectively a spillover table for large objects. Indexes can use toast, but you generally don't want to do that because that significantly slows down index access because it has to walk down to a point and then hop over to the toast table to get the full value. And it requires a totally ordered type, basically a type that supports equality greater than or less than for all values. Many, many data types, including very important data types in Postgres, are not totally ordered and thus don't really work in these. Okay, so that's B-tree. Save that and we'll go on to hash. Hash indexes were long broken in Postgres. For a long time, they kind of just didn't work very well. They weren't wall logged, so they weren't crash safe. They were a forgotten feature, which is a shame. Postgres 10, they got fixed. They work just fine now. It takes the input value and converts it to a 32-bit hash code, and with a hash table that points to buckets of row pointers, kind of like every hash table in the universe. It only supports one operator, equality. But that's a pretty important operator. You use equality a lot in databases. So the indexes are much smaller than B-tree indexes, especially for very large types, because it only has to store the hash code. It doesn't have to store the full value. It goes out to the table to get the actual value. And if there are few collisions in when you're doing the index, the access can be faster than a B-tree. It's really good for long values where the primary thing you're doing with them is comparing equality. This is a very large set of things, long character strings like URLs, things like that, even UUIDs sometimes. It's sort of ironic that you end up hashing something that's already a hash. Excuse me. But for example, if you have SHA 256 hash values, you may not want to use a B-tree on them. You may, since greater than or less than doesn't mean anything for these, you may want to just hash them again and put them in a hash index. Just index it. Yes, sir.
What would you consider a long value for a string?
It's a good question. I would say around 2,000 bytes. Make me justify that under pain of torture. I can't. But 2,000 bytes is kind of where my gut tells me time to start thinking about other index types, because that's about the point that things start getting spilled to toast. So, in fact, there's a compiled in constant in Postgres of 2,000 bytes. So, gist indexes. First of all, gist isn't a specific index type. It's a framework to let you write your own indexes. It's a generalized framework. In fact, that's what it stands for. So, because Postgres is always throwing in new types of all kinds, and sometimes you want to write your own types. You can go through all the trouble to write a full-on index access manager, which is a pain in the neck. Don't do that. Or just makes it easier for you. And what a gist index does depends on the particular type being indexed. So it's a little bit abstract. It depends on what you're actually indexing. But the most common use case is this. So we have a point, and we have a rectangle, and we have another point. And we want to index these. But what does that mean if we're talking about B-tree indexes? I mean, a rectangle isn't greater than or less than a point. You know, equality makes sense if they happen to be exactly the same kind of object and thing, but that's a fairly restrictive operation. You know, is this point greater than this point? I mean, you know, what does that mean? But inclusion makes total sense. You know, this point is inside this box. It's a really big point. So we have that. That's a completely reasonable operation, and of course, in geometric databases, it's an extremely common one. So just stands for generalized search tree. Yeah, talk about your forced acronyms. And it's generally used for any type where containment or proximity is a meaningful operation. In fact, standard total ordering can be considered a special case of proximity. I'll proof left to the reader. And this is a lot of things like ranges, geometric types, text trigrams, all these kinds of things. And Postgres makes heavy use of, make perfect sense to talk about, is this inside this or is this close to this in some kind of geometric space? It's not as efficient for classic scalar types like int with total ordering or for simple equality operations. The generality of just does come with a price. Okay, so this is the first survey. We'll talk about when exactly you use each one in a bit. GIN indexes, which is short for generalized inverted index. The problem is that both B-tree and GIST tend to perform poorly by comparison, where there are lots and lots and lots of identical keys. However, full text search, you know, which is the most classic case, has exactly that situation. You have a relatively small corpus of words, and you know, compared to a gigantic amount of things you want to index that use them. You know, there are what? In you know, typical conversations, there's about 5,000 to 8,000 English words we use all the time. There are a lot more English words that you walk into the library and look around. So, thus, GIN indexes. GIN indexes organize the keys themselves into a B tree, and then the leaves of those B trees are pointers to lists or further B trees to the rows that hold them. This scales really efficiently for a very large number of identical keys. So full text search, if you're indexing an array and you want to look up, like you have a bunch of arrays and you want to say, find me all the rows where this array field contains a 5. That's a very efficient use. JSON objects where you're indexing the keys, things like that. SPGIST, who has ever used an SPGIST index? You notice I'm a consultant who does Postgres all the time and my hand is down. Yeah, it's a shame because it looks really cool, but not as many use cases for it. No, I take it back. I've used one. Yay, that's wonderful. It's similar to a GIST in concept. It's a framework for building indexes. It has a different range of algorithms for how it partitions up the space to build its index than classic GIST. It's mainly designed for situations where a classic GIST would be highly unbalanced. And we'll talk about one use case for this later. Brin. This is possibly the neatest alternative index type that people don't use yet, but it's really powerful and wonderful. Block range, it's short for block range index. B-tree indexes can be very large. It's not impossible for the B-tree index, for a single B-tree index to be as large as the table is indexing. The indexes in aggregate on a table are often very, very much larger than the table itself. Because B-trees are completely general. It assumes there's no correlation between where the row, where the key value happens to be and where the row physically is on disk. So they can be randomly sorted, doesn't matter, B-trees work fine. But often we do kind of know. For example, this very, very common Postgres idiom, where you have a created at timestamp, that every time you insert a row, it gets stamped with when you put it into the database. Insert-heavy tables often have monotonically increasing keys like this, serial primary keys, timestamps, things like that. And if the tables aren't update-heavy, like let's say it's a log, where you're really never changing a row once it goes in, the key will tend to be strongly correlated with the position of the row in the table. So further, as you go into the table, that key will just keep increasing. And Brin takes advantage of that correlation. So instead of a tree of keys, it records ranges of keys in the pages that probably contain them. So it says key 1 to 1 billion are probably in this row, this block. So go into that block and find them. It's much, much smaller than a B-tree index. And by much smaller, a B-tree index that is, assuming that the data works well with Brin, a B-tree index that is in the gigabytes can frequently go down to the kilobytes in Brin. So it's multiple orders of magnitude smaller. And if this correlation assumption is true, then it can be much faster to retrieve ranges like get me all of last year's orders than a B-tree. But it's not good for heavily updated tables because every time you update a row in Postgres, it moves to somewhere else. Small tables, because you don't get much traction for these ranges. And if there's no monotonically increasing key, Brin has nothing to grab onto to make to work. The last one is Bloom indexes, which are, this is an extension, this is in Contrib. Little used, but it actually has a very powerful, very common use case. It's like a hash, only different. So it's most useful for indexing multiple columns at once. It's very fast for multi-column searches, such as if you have a bunch of attributes on a thing expresses their own column, and then you index them all together with a Bloom index, it can be very fast. And it's very, very small compared to creating a B-tree index on each column individually. And it's potentially faster for retrieval for a very large number of attributes.
You mentioned that it's like a hash. Does it actually hash?
Yeah, it does. It does. It takes all the values and hashes them together. It's also insensitive to the order of attributes, unlike a B-tree, where a multi-column B-tree index is very sensitive to which order you put them in the index. Bloom indexes are insensitive to that. So, now that we have our toolbox, how do we use it? Well, the first question we should ask is, do we need an index at all? Indexes are expensive. They slow down updates, they increase the disk footprint, they slow down backups and restores, all sorts of things that are bad about indexes. So as a very rough rule of thumb, an index will only help if less than 15 to 20% of the table will be returned on a query. After that, it's often cheaper to just do a sequential scan because walking an index is expensive compared to just scanning the table. So the usual reason that the planner isn't using an index is it thinks it's more expensive than doing a sequential scan because of the number of rows that comes back. Sometimes it's wrong, and then it's time to do some debugging. You have to have good statistics for proper index usage. So make sure that tables are getting analyzed and vacuumed properly. Consider increasing the statistic target for specific columns, not globally, just specific columns that have a lot of distinct values and more distribution than 100 buckets, which is the default, can capture. UUIDs, hex hash values, tail entropy text strings, text strings that are like very, very, very constant, and then once you get out to column, character 4000, it starts getting really random. Don't jam up the statistics across the whole table. You won't get that much advantage out of it, and it will significantly slow down how long it takes to analyze the database. So who's on RDS? Who's done a push-button upgrade on RDS from one major version to another? Who had their database lose its mind immediately after that? Right. When you do an upgrade or a restore, you need to run a database-wide analyze all to rebuild the statistics. In community Postgres, when you use the PG upgrade tool, it writes out a little note saying, oh, by the way, here's a script, please run this. It does that on RDS too, but it doesn't tell you and it doesn't let you run the script. So you have to go and do it yourself manually. This has happened for 3 separate clients in the last 2 weeks for us. So it's not an edge case. You can have really bad statistics even though you're doing everything right. So let's say you have 100 million rows, 100 buckets, the default. The field is not unique, but there are only 25,000 unique values. This is not uncommon in a foreign key field, for example. And then you say, OK, I'm going to select everything from T where the sensor ID is this big, where is this UUID. The planner is going to think 1 million rows come back, because these are pretty much randomly distributed, and they're landing in 100 buckets. And it's going to extrapolate from that to what it thinks is going to happen. And it'll say 1 million rows. And thus it'll say, well, maybe I don't want an index here, to use an index. Maybe it'll be just cheaper to do a sequential scan. And it's wrong. So this is a great case where bumping up the statistics can get you a better plan. Last, indexes and multi-version concurrency control. Indexes store every version of a tuple until vacuum cleans up the dead ones. So as you update, if you update a row 50,000 times, you're going to have 50,000 dead tuples, both in the heap and in the index. There is an optimization Postgres called hot, which does optimize this to a certain extent, but not completely. And it means that in the normal case, an index scan has to go back out to the heap, to the table itself, to determine if this is one of the live tuples that it can see. So this can really slow down index scans. It can, in fact, break index scans sometimes in a really, really heavily updated table. And really heavily updated tables happen more often than you might think. For example, if you have a job queue or something like that that's being updated and inserted and deleted from all the time, that counts. So the index bloat can be quite significant there. So so you have to be aware of this. Make sure you stay up on your vacuuming. It sometimes makes sense to just rebuild the indexes. You don't have to take you don't have to do a reindex operation necessarily. You do a create index concurrently for an identical index and then drop the old one, for example. So if you have that kind of heavily updated table and queries seem to be slowly falling apart, take a look and see how bad the index bloat is. Postgres does have an optimization that helps here, which is if we know that the tuple on every page is visible to the current transaction, we can skip going to the heap. And Postgres uses the visibility map to determine this, which is a very big optimization. And if the planner thinks enough pages are completely visible, it'll generate an index-only scan operation. This is nothing you have to do. The planner just does this. The only thing you have to do is make sure you keep up on your vacuuming. So always make sure you leave auto vacuum on, make sure the tables are being updated vacuum frequently. Index scans kind of come in two types. There's lossy and lossless. Some index scans are lossy in that it says, well, there's something probably matching on this page on disk, but I don't know which exact rows match. So I'm going to fetch the whole page and filter it, which means it has to retrieve the pages, scan them again, and throw away any rows that don't match. If you are looking at an explain plan, the most common version of this is bitmap index scan and bitmap heap scan. The bitmap index scan builds the list of pages. The bitmap heap scan goes out, grabs the page, and sees what matches and what doesn't. Some index types are inherently lossy, like gin and gist are inherently lossy. A relatively new feature in Postgres, which is pretty cool, other databases like Oracle have had it for a while. Queries often return columns that aren't in the index predicates of the query. Frequently, you're grabbing other fields out of when you do a query. I mean, that's pretty common. Traditionally, Postgres had to go out to the heap, grab the page, and get those extra rows because they aren't stored in the index, so it had no other place to get them from. A feature was added in Postgres 11, which you can add non-index columns to the index, and they're retrieved directly when the index is scanned. So it doesn't help on non-index only scans, so make sure your vacuuming is good. And remember, you're increasing the size of the index because you are putting these things in there, so don't go crazy and just slam every row into the index. Yeah?
So on this, how much is the difference when you just have a multi-column index as well? So if you do a name and address, and then you have a covering index that says name, and then
It doesn't help that much it doesn't help any on size. It does help on insert time because it doesn't have to do the sortation. Because
that's the only difference.
Yeah, that's basically the only difference. So gin indexes. Gin indexes are very, very fast to query, but they're much slower to update than any other kind of index because you have all these B trees that you have to mess around with. And sometimes you have to make decisions on when to break pages and do all this kind of stuff. It's slow enough that Postgres doesn't actually update the index immediately when you do an insert. It stores them in a separate posting area and updates the index at vacuum time or on demand. A very frequent situation we'll get is somebody with a table with a very heavily updated gin index will suddenly have the system kind of go crazy on vacuum. And what's going on is it's resolving this posting list. One thing you can do is you can tell it when to clear the pending list. The pending list and posting list, same thing, by calling a function. So you may want to do that. For example, if you do a giant batch update to a table that has a gin index, you may want to call this function immediately after to resolve the pending list. B tree alone currently supports unique indexes. If it's perfectly fine to do optimistic insertion on with index and recover on an index conflict. Like if you could say, well, I'm going to insert a bunch of things and maybe it exists and maybe it doesn't. I'm just going to try, and if I get an error, well, it existed already, so that's fine. That's a fine strategy. Postgres does have a function. You can do an insert on conflict, do other things. That makes that much easier. One thing to be aware of is it can be a concurrency killer, because Postgres has to go and lock pages to make sure that if two separate processes or sessions are trying to insert the same row, that only one succeeds in the event that they both try and commit. So if you have for example, let's say you're collecting sensor data. That's a very common thing, and for some reason you have a unique index on the table you're inserting into. Maybe not the best idea. If you have 1,000 inserts per second and 100 processes doing that, you're going to get some serialization and bottlenecks on this locking. It will definitely be visible, so be aware of that. B-tree indexes also have a generalization of unique called exclusion constraints, which is only one value that passes this comparison is allowed in this table. This is very handy for things like the hotel room reservation problem. You only want one row. You don't want somebody to be able to insert two rows into a table where they both have the same room number and they have overlapping date ranges. There's no way of doing that with a unique index, but you can do it with an exclusion constraint by using the overlaps operator on the date ranges. That's very nice. Okay, so now we're going to talk about, so now we have these zillion indexes. Which one should we possibly use? How do we decide which index to use in a particular situation? First, gather some information about the situation. The typical queries you're going to be doing, the columns and the data types and the operators that you're using in these queries, including joins, and how many rows the queries typically return. So have that in your head when you're making these decisions. So does the query typically return a large percentage of the table, like 50% or more? And this includes hidden row fetches such as count star, which in effect has to query every row and pick up every row in the table. If so, you probably don't need, probably an index won't help. Figure out a different way of solving the problem. You can refactor the query, consider summary tables or other techniques before just throwing an index at the problem that didn't actually help. Very small tables that fit in memory probably don't need indexes at all except to enforce constraints. So if you have a table that maps California, two-digit state codes to state names, you probably don't need an index on it. So if you have more than one predicate, where this equals this and that equals that, which columns are being used? So always start with the most selective one, the one that will cut down the result set the most. If the indexes individually don't cut down the results much, but together they cut them down a lot, the intersection is very small, that's a good sign you want a multi-column index. So if A equals 1 returns a lot, and B equals 2 returns a lot, but B equals 1 and A equals 2 returns a very, 1%, then you probably want a multi-column index. Yes, and we will talk about that. So, but first let's consider the single column case. Is the column a small scalar? These I would all call small scalars. Int, big int, float, UUID, timestamp TZ, inet and char types we'll talk about later. Is the value a primary key or otherwise unique? Then use a B-tree. That's your choice right now. Is it monotonically increasing on a large, rarely updated table and the query is doing a range operation? This is a pretty common kind of thing for things like summary tables, data warehouses. They do this kind of stuff all the time. Consider primarily a Brin index. Otherwise, a B-tree. That's the right index type for this kind of stuff. If you're creating it primarily to support order by descending, then create as a descending index, otherwise ascending. Postgres can walk an ascending index backwards, but it's not as efficient as walking a descending index.
What is the impact of if I have some columns with a lot of null values, how do these indexes treat them?
You can index null values and have where is null. So you should just consider them like any other value, really, unless you exclude them specifically with a predicate where is not null, which is a very common operation. So, is the column a text field, like varchar text or char if you're weird? There's really no reason to use char. I really wish Postgres had a true fixed width character type, but it doesn't. So are you doing full text search, trigrams, or other fuzzy search techniques? That's a trick question. We'll talk about that later. Is the data structured and prefix heavy, and are you typically doing prefix searches, like URLs are a good example where you're searching primarily on the host portion of a URL? Then spgist actually works really well for this. This is what spgist is designed for these prefix-heavy searches where there's not a lot of entropy at the beginning of the string. If it's a small value, let's say 200 characters. I said 2,000 earlier. I'm saying 200 here. You can tell I don't have a fixed opinion. Or do you require total ordering? Like, are these for some reason things where you have to say greater than or less than? If so, use a B tree. Otherwise, consider a hash index for these. This is what hash is good at. Is the column a bytea? Just a big byte blob. Postgres allows this. Why are you indexing a bytea? Please don't index byteas. Please. If you must, use a hash or calculate a hash values and store it separately. And then, run through the decision tree again based on what the hash value, the characteristics of the hash value. Postgres will let you create this index, by the way, but why? And if you're doing this bytea greater than that bytea, I would love to hear about your use case. Is a column a range or a geometric type? This is what gist is there for. This is why we have gist. Like PostGIS, the Geographic Information System extension for Postgres. These are all gist-based. If you need nearest neighbor searching, you want to use gist for sure. This is what sometimes called the Starbucks problem in geoinformation systems, which is you think, what is the OR use case for a geometric is get me my nearest Starbucks. But if all you have is containment, this is actually a really hard problem. Because if I'm sitting here, in this hotel, and I say, get me the nearest Starbucks, there are probably a lot of them within a mile. Probably a lot of them within a quarter of a mile. If I'm out in the wilderness in Montana, it's a much bigger search. So how do we decide what that initial bounding box is? And this is a hard problem in geoinformation systems. Postgres has an index type called KNN that specifically solves this problem without you having to pick a bounding box. So that's really handy. If you have a very, very skewed distribution where the data points are not particularly random, spgist is sometimes a better choice. So experiment with both and see which you get better performance on, assuming spgist supports your data type. Are you indexing inets, which is a generalized internet address for both IPv4 and v6? Are you just doing equality? That's the only thing you're going to do. B-tree is probably the best one for that. Try hash probably isn't going to be better, but you can try it. Are you doing prefix searches? Searching on CIDR subnets and things like that. Consider spgist. This is actually kind of the OR use case for spgist because IPv4s and v6s are most definitely not evenly distributed across the range of possible n-bit values. Are you indexing an array or a JSON-B? Are you just doing equality? Do hash. Works really well. Are you searching for key values at the top level within the object? This is actually an error in this slide. You can, or it should be just key values, period. You can index any depth. Gin is there for you. If you need keys from inner values, you can use expression B tree indexes, or now you can use gin. This is obsolete information, my apologies. Is the column JSON with no B? Postgres has two different JSON types, JSONB and just plain JSON. Why is the column JSON? It's obsolete, you should not be using this. Your only option is expression index because you can create a B tree index on it, but the only thing you can do is equality. There are a couple of edge case reasons to use JSON, I'll just mention them. One is if it's insert only. You're just logging raw values and you are basically never going to search or rarely going to search. JSON is a little faster to insert than JSONB because it doesn't have to parse it and do all the encoding for it. And the other is if there is broken JSON out there in the wild, like it has the same key twice at the top at the same level of object, and JSONB doesn't handle this, but JSON does. But if you need real powerful indexing, far better to convert it to JSONB because JSONB works much better. Are you doing full text or fuzzy search? If you're doing full text search, create a TS vector from the text and create a gen index on that rather than indexing the text directly. TS vector is the encoded and takes it, runs it through a dictionary, turns it into, tokenizes it, does all that stuff for it. You can either store it as a separate column or use an expression index. Frequently you'll want to store it as a separate column because you are actually going to smash multiple columns together into the TS vector. For example, if you might want to have an author, a title, and a body with different weights, and you calculate a TS vector from all of those and all that, which I just say in the next bullet point. If you're doing fuzzy search, like with trigram, create an index on the column using just trigram ops, which is part of the trigram package. This is really nice for things like auto suggest from a drop-down list because it's really, really fast. So, and if you're doing a search on every time someone types a key, that's important. Is there more than one column in the predicate? Consider creating a multi-column index if the predicates together are highly selective. Remember, if you create an index on A, B, Postgres will almost never use it for just a search on B. It's funny, like the day before I was working on these slides and I said never there, I saw a query that reused B. It was a really bad plan, and I'm not sure why it did it, but it did do it, so I can't say never. So find the right index type for each column individually and create the index based on the most selective column. One catch here is if some of the columns need a gist index, the whole thing has to be a gist index. You can't mix and match the top level, the index type within a single index. Fortunately, you can install the btree gist package so you can get gist operators for things like int and basic operations. So if, for example, you have an integer and a range, you can create a gist index that uses both. If the query pattern is an arbitrary combination of comparisons on the various columns, consider a Bloom index. This is actually a more common use case than you might expect. For example, you have a GUI that says search that has 12 different predicates you want to search on, and the user gets to just type them. That's a really hard query pattern to optimize. But a Bloom filter is probably your best bet there. If the predicates are selective individually, you might want to just create an index on each one. Postgres can and or index results together. But you want the individual ones to be selective in that case. Does the query contain an expression? Consider creating an expression index. For example, an index on an accent lower name instead of querying on it. That can be faster. Sometimes it's better to create a different, a separate column that handles this, like a column of case-independent text for the lower part. Just make sure you're using that query, that particular expression in the query a lot, because it's going to be expensive to build and maintain this index. So make sure you're getting a good value out of it. If you index on a user-written function, now we're getting into some pretty advanced stuff, but you can do it. Make sure that it really is immutable, that you just didn't declare it immutable because you don't know what immutable means. Roughly, an immutable is a pure function. It can only depend on its inputs. It can't depend on the state of the database or the state of the system. This can be you can sometimes fall out of immutability in weird ways, like doing time zone operations, because time zones are not immutable. Is one predicate highly selective? So, like this, where only 10% of the orders are active. Consider creating a partial index, like that. Because it'll only index rows that contain where that predicate passes. So this can really speed up operations, especially if this part evaluates to a very, very small subset of the number of rows. Because you're not only are you searching through it because it's a much smaller index at that point. Okay. How do we answer the question, do we need an index? Well, look at pgstat user tables. You can look at tables with significant number of sequential scans. That's a good place to start. Not all sequential scans are bad. Look at the particular queries, look at their execution plans, decide what you're going to do. You can look at PG stat statements and the text logs, and PG Badger are your friends here. Once you created an index, is it actually using this? Well, you can look at PG stat user indexes and see how many times it's being used. Drop indexes that aren't benefiting you. Indexes are expensive to maintain, so don't have any more than you need. Are indexes bloated? Indexes can suffer from bloat, just like the tables can, sometimes worse. Vacuum can't always reclaim index space as efficiently because indexes have structure, unlike the heap, which is just big bag of tuples. Sometimes you do want to rebuild indexes. We have you can just don't have to handwrite this, copy down the slide. We have our favorite bloat check for indexes. Sometimes indexes, yeah.
What amount of bloat would you find concerning your ratio?
I generally don't get upset about less than 50% bloat, at less than 50% bloat. 50% or more, I think, is acceptable by some stretch. It depends a little bit on how, if 50% bloat on a gigantic index is a little worse than 50% on a smaller one. But really, it depends on indexes. Really, it depends on query execution time. If you start noticing slowdowns in query execution that you can't explain any other way, then that's a better guide.
How are you defining bloat on the indexes?
In this case, I'm defining it strictly as both dead and free space, because it's a little harder to tease out those two apart. So.
Yeah, well, the feature index specifically, if you're doing a lot of kind of randomized updates, the theoretical density of the index is going to be somewhere around 50%.
Yeah. So. Look at the query. And I'll have to go back and look at the query to remember exactly how it works. But that's why I say, really, it's more of a performance-based thing. If the query is running fast, I don't really care how much dead space there is on it. Indexes do get corrupted sometimes. Doesn't happen very often. Happens a lot less than it used to, which is great. Sometimes you'll get an error during a query that'll it'll say something bad. Postgres 10 Plus has amcheck as part of contrib, which will let you actually check the structure of the query. Fortunately, if you're starting to get errors, it's easy to fix. Just drop and recreate the index. And to conclude, indexes are great. Yay, indexes. Just remember they're an optimization. Always create in response to a particular query situation. Don't just throw indexes at a table hoping they'll help. And experiment. Test different types of indexes. See what works the best. And don't just go by B tree by default. Pick the right index type for the data. Postgres has all these great indexes. Use the right one. And monitor usage and size. Keep the database healthy and trim. And thank you very much. Any further questions? Yes, sir.
So if I have queries that happen exclusively on a read replica, and I can only create the index on the master, is there a smarter way to index that query that happens with a read replica?
Yeah. The schema has to be 100% identical. Now, something to think about is if this is a big problem for you, consider moving to a logical replica instead of a binary one. Because a logical replica can have any schema you want, assuming it can still, figure out how to do the insert. So that's a lot of there are a lot of problems that used to be related to binary replicas in Postgres, where the answer is now think about firing up a logical replica instead of a binary one. A lot of data warehousing and things like that. Query cancellation issues on heavily read from replication. Some kinds of replication lag. Logical replication has intrinsically slightly longer replication lag, but on heavily queried databases, it's a little bit more controllable. You don't get the query cancel. You don't get that balance between replication lag and this trade-off between replication lag and query and query volume that you do on a binary replica. So there are a lot of good things about a logical replica. Increases your sysadmin overhead a little bit, but so. Any other questions?
You might want to mention text pattern maps.
Oh, right. What should I say about text pattern maps? Here, Mr. Conway will tell you about text pattern ops.
Well, if you're using a
My brain's
index and you're doing light queries that are
Yeah,
on
right.
there.
Sorry.
So you can like, like percent, some constant percent. type of
Yeah.
thing. And you set
The default pattern operator, the default operator, if you create it on a text type, if you create a B tree, doesn't support like type operations like regexes or the like percent operations. There's a separate operator, text pattern ops or varchar pattern ops, that does support that. There's no reason not to use that actually, because it supports equality and the rest of them just fine. There was a time that you had to create both if you wanted them to be both. You had to create both if you wanted to use both standard ordering operators and fuzzy searching, or it's not fuzzy, pattern searching. That's no longer true. So, thank you for the reminder. Anything else? Thank you very much.